Another exponential function that we're going to be looking at quite frequently throughout this course, and for those of you that have to take calculus and higher, is going to be the natural exponential function. And before we talk about the function itself, we need to discuss what the natural exponential base is. So the natural exponential base e is going to be this expression, 1 over 1 plus 1 over n to the nth power, excuse me, as n approaches infinity. Okay, now e is an irrational number. And eventually what's going to happen is E is going to get to 2.718281827. The natural exponential function f of x is e to the x, right? So now before we go there, I just want to make sure that everybody understands that, how we arrive at this number, the 2.718, etc., and then also how we can use the calculator to approximate this. So what I'm going to do is I'm just going to throw some big numbers in for n, okay, into a scientific calculator. All right, so let's say we plug in 1 plus 1 over 100, and I'm going to raise that to the 100th power. All right, so I get 2.704. And remember, what we're trying to get to is we're trying to get to this 2.71828 approximately. So let's add another 0 in there. Okay, and we get 2.716. Let's add a couple more zeros. So 2.71826. Let's add just a couple more zeros. All right, so 2.71828. And so we could see 2.71828 and then 1827. If we really wanted to get there, we could add like 4 more zeros. All right, and we keep getting closer and closer to that number. I'm just going to keep adding zeros in there. Not sure what happened. Maybe I added not enough zeros or something like that. So, but you get the picture. I think I just added too many zeros at some point. All right, so that's the natural exponential base, and that's where this number comes from. One of the first things we have to do is we have to make sure that we can use a calculator to approximate e to the x, okay? So f at 3 is really just going to be e cubed, right? And we're going to approximate it to 5 decimal places, it says, okay? So in my graphing calculator, now for Desmos, for those of you that are using Desmos at home, what you're going to have to do is you're going to have to go to func, F-U-N-C, for function, and here's your e, okay? So it's going to be e to the third, okay? That'll be 20.08554, okay? So 08554, so that's going to be 20.08554, okay, if I was to approximate it, okay? If you're in your TI calculator, if you have a graphing calculator, it's usually on the left-hand side, okay? And what I'll do is I'll make another video to illustrate how to try to input these by using a graphing calculator. F at -4 is going to be e to the -4th power, and so that's going to be a small number, okay? So because it's going to be 1 over that 2.718 to the 4th power. So let's just go into our graphic calculator to see what that looks like. So I'm just going to change this to a -4. And it's going to be 0.01832. Okay, so just going up to here, 0.01832. Right, so that's going to be 0.01832. All right, and then finally, f at 0.13, that's almost f at 0, or e to the 0. All right, so it should be a number fairly close to 1. All right, let's see what happens with this. So we have e to the 0.13. All right, and we get 1.13883. All right, so forgot what it was, 1.1383. All right, so that's our approximations. And that's how we can try to approximate e by using both the original function, but then also to be able to approximate the function f of x equals e to the x. All right, and like I said, in another video, what I'll do is I'll show you all how to use this on a graphing calculator, not just Desmos. All right, now let's see what the function e to the x looks like. Okay, and ones that we can fill out right away. Okay, we know that at 0, 1, okay, because we would just substitute 0 back in for that. And then also at 1, we already know what that value is. All right, we substitute it back in. It's the 2.7. I'm just going to go to 2 decimal places. All right, so that's going to be 2.7. And I believe that we found at 3 already was 20 point, I think it was 0 or 6. Let me go back into the graphing calculator and do E cubed. It's 20.1. Okay, so that's going to be 20.1, which is going to be off our screen, which we're not going to worry about. Oops, it should be down here in the cube. That's 20.1. Now we're going to have to go back to our graphing calculators for the rest of these, okay, or scientific calculator. So if we throw in e squared, okay, 7.4. All right. And then -1, that's going to be 0.4 about. And then -2, that's 0.1 about. And then finally -3, 0.05. All right, so, all right. And then I'm going to zoom in just a little bit so that way we can go ahead and graph this, not rotate it. Okay, so at 1, it's about 2.7. So we have this point right here. That's our easy point. And then about 2.7, which is right about here as best as I can. All right, that's not too terrible. It's not too good either. And then we have 7.4. So maybe like somewhere up here. Okay. All right. I'm not even going to try to plot the 20.1. But we have -1 and 0.4. So maybe right here. Okay. And then it's keep getting closer and closer to the axis. All right, ignore that one that's below the axis. Sorry about that. I'm sure I could zoom in just a little bit more to get a better picture. All right, so let's do that. So right there. And so our function, if I were to zoom back out, our function looks just like a regular old exponential function. Okay, so it's going to do something like that. All right. If we wanted to find the domain, not that I asked you for it, but the domain is all real numbers. All right, so that would be from -infinity to +infinity. Right? If I were to ask for the range, that would be from 0 to infinity. As we can clearly see, it's approaching 0 from as x goes towards -infinity. And then finally, for the asymptote, y equals 0 for this. One last thing that I'm going to do with this is I'm going to graph 3 functions. I'm going to graph e to the x, 2 to the x, and 3 to the x on the same graph. Okay, so I'm going to say y equals e to the x. And just a heads up, sometimes in computer programming, for those of you that are computer scientists, what happens is a lot of times they'll use exp of x to represent e to the x. Okay, so if you ever see e to the x or exp to the x, they mean the same thing. Okay, so you notice right here, that's the same. If I delete that, okay, there it is, there it is. Okay, so again, just making sure that if you ever see exp in computer programming, we use that quite frequently just so that way we don't have to deal with the exponents. Okay, so let me plot y equals 2 to the x, okay, and then y equals 3 to the x. I want you to notice that e to the x probably behaves pretty closely to 3 to the x. And you probably remember that we said e is about 2.71828. Okay, so remember, if I wanted to plot, let me get rid of these just for fun. Y equals 2.71828 raised to the x. All right. And notice that these, like the blue line is almost the exact same, or the green line, excuse me, is almost the same as the black line. All right. Just because these numbers are really, really close to one another. Okay. So just verifying that was the number that we got for this. Okay. So that's the natural exponential function. Pretty cool. And that's the graph of it. Just behaves just like a regular exponential function, pretty close to 3 to the x. Okay. So if you ever want to kind of, in your mind's eye, imagine what e to the x looks like, just plot 3 to the x and you'll get a pretty close description of that. Okay, so I will try to make a video. In fact, I will make a video of how to use a graphing calculator, like a TI calculator, to be able to get e to the x and then also plot it and things like that. But one last thing that I want to do in the next video is I want to use the transformation rules to be able to move the e to the x function around a little bit. Okay, so we'll see that in the final video, and then also take a look at domains, ranges, and asymptotes.